Dealing with weak bases is very similar to dealing with weak acids. However, when you run your calculation through, you're going to get hydroxide ion concentration. And if you're getting pH, be careful. You'll have to then convert that POH to pH, that kind of a thing. Let's take a look at what's going on. Imagine we've got ammonia. Now in water, ammonia is a Bronsted base because it dissociates a little bit, forms the base just a little bit, I think is the way you would say it. It's not really dissociating, is it? NH3 is forming NH4+, which is a weak acid and a stronger base, so overall this thing is basic. Another way of recognizing that it's basic is that once you throw it in water, it forms hydroxide. So it's a base in the Bronsted, but not the Arrhenius sense. There is no OH minus present in pure NH3. It generates it once you throw it in water. Fine. But it doesn't do it that much. This reaction goes forward a little bit. It's mostly just staying like that. We need to know the ionization constant, which is equal to this value, in order to get an idea to what degree this reaction is moving forward. And the higher it is, the more the weak base strength will be. And I don't know if they give it for this thing. That's frustrating. I think it's about 10 to the minus fifth. So we solve them, but remember you have to do a calculation to go from hydroxide to H plus at the end. Let's go ahead and solve the problem. What's the pH of a 0.4 molar ammonia solution given that its Kb is 1.8 times 10 to the minus fifth? You have to start by writing the reaction, and sometimes people start doing weird things where they take NH3 and they take a proton away from it, but notice we're given a Kb, and that is what happens to water. You should also know that's what happens to ammonia when you throw it in water, is it forms ammonium hydroxide. And there is its Kb. It is around 10 to the minus fifth. So write the reaction that forms base, since this is what they're giving you a Kb, and you should know that that's what ammonia does anyhow. So you write the chemical reaction. We write the equilibrium constant expression, which would be ammonium times hydroxide, and they'll each go up by a value of x, leading to the x squared here. They did give you this. And then this will be 0.40 minus x. And if we could, we're going to have to approximate it, it looks like. Why don't we have the water value here? Well, it's not in solution. It's pure water liquid. That gets omitted. Omit solids and liquids. We could solve for x at that point, and would we be done? No, we'd still have 2 steps left, right? That would be the hydroxide concentration. So we'd take the negative log of the hydroxide concentration and give us the POH. Subtract that from 14 to get the pH. Okay, let's take a look at the longer way of doing this, which is a nice table. Write the chemical reaction. Oh, there it is, right? So we did get the hydroxide. We took the negative log. We did get the pH. Yay! The ice table, let's write down everything we know. It started as 0.4, and now's we're nothing. It's going to go down by a value of x. Those go up by a value of x. We take the approximation as always and remove that negative x. We solve mathematically. We get our hydroxide concentration. We take the negative log to get the POH. We subtract from 14 to get the pH. That's a little bit about weak bases and a sample calculation for that.